start the recording here, make sure I capture that. So that's the nice thing about academic life is that the semester is finite. I know it may not feel like it right now, but it will end one way or another. It will come to an end. So it's up to you how quickly you want that to happen. But I will tell you your last homework, which is due at the end of finals week, is over invariance. So given what we've talked about already, you can do half of it right now, and hopefully by the end of this week, you'll be able to do the whole thing. So you could get it done as quickly as you'd like and have your semester be over. So any logistic homework questions, anything like that? No? How about we review? Rather than staring at PowerPoint, let's stare at something prettier. Rocks. There we go. That's a better picture. So what have we been talking about? What did we do last week besides eat frosting? No, that's what I'm going to do next week.
We walked through all the steps
The
for
steps.
testing like invariance, like it's measurement and then structural.
Yeah. So measurement invariance has to do with how the items relate to the trait. So the factor loadings, the intercepts, the residual variances, as well as any residual covariances. Then we get to structural invariance, which has to do with the summary statistics for the traits. So whether the factor variances, factor covariances, and factor means differ across groups. Yes, we did Latent Anova at the end of the last class by testing whether or not each factor had a different mean across groups. That's what we're working on. So the steps themselves, just to give you, put our heads back in the game here with respect to how to actually execute the steps, we start with a model that's called configural. In that model, if you have two separate groups, as in this example, each group gets their own everything. So all parameters are different between groups. We're just estimating both models simultaneously so that we can get a sense of their joint fit. And in this model, I have it identified such that each factor has a mean of 0 and a variance of 1 in each group. So each group is on a different scale. They are not comparable in any sort of way. And from this point, are we going to try to make our model fit better? Are we going to make it try to fit not worse? Yeah, it's the latter, not worse, because we are taking away parameters. We are trying to save estimated parameters. We're trying to constrain things to be the same. So we're taking stuff away. So we're going to do -2 log likelihood difference tests, likelihood ratio tests as they're called, in using maximum likelihood, and see whether or not the model fits worse or not worse. So questions. Oh, here we go. If we have more than 2 groups, do we have to make the groups binary to test invariance, or can we have 4 groups? You can have 4 groups. It's just that then there's more possibilities for how something can be non-invariant, because you could have group 1 differ from 2, or 1 from 3, or 1 from 4, or etc., etc. So troubleshooting non-invariance will take longer, but in theory, you can have as many groups as you're willing to have the patience to test through. Next question, can we talk about latent ANOVA again? I think that was cut off from the recording. So at the structural invariance stage, we would test group differences in the factor variance, so whether we could make the factor variance the same between groups and not make the model fit worse. The factor covariances, if there are multiple factors in the model, can then be constrained. And the last step is the factor means. So I had referred to this as latent ANOVA, in that typically we would look at mean differences as a function of a grouping variable and some sort of quantitative outcome as what ANOVA is. The difference here is that we are looking at latent variable means. So latent ANOVA, the mean of the imaginary variable that is represented using the observed information. So the covariance in common gets a special name. We call it a trait. So yes, like latent ANOVA. Okay, other questions before I jump back in? Keep them coming. I like questions. Otherwise, it's just me talking to myself in my basement, and that's no fun. I do that enough as it is. So configural is the first stage. The next stage, metric, is what it's called. Metric invariance is a test of whether the loadings are the same. This one's super important because it refers to the definition of the factor, like the way that people want to interpret, okay, what is this latent variable, right? Because we just made a circle, and it's up to us to provide some sort of interpretation for what trait the circle is supposed to refer to. And the way that the items relate to the trait is often how people define what the trait is, especially in exploratory models, but still in confirmatory models. If some items load more highly, you would think that the trait has more to do with those highly loading items than lower items. So metric invariance is the idea of whether or not the items are measuring the same trait in the same way. Are the items that are relatively high the same across groups, and the items that are relatively low the same across groups? At this stage, when you constrain the loadings to be the same, you have to release the constraint on the factor variance. So in the alternative group or groups, the factor variance is estimated. It's still fixed to 1 for identification in the reference group. So you'll always have one reference group. You can have as many alternative groups as you want to have. So the reason for that is otherwise we're putting a structural constraint and a measurement constraint at the same time. If we force the loadings to be the same, then whatever differences were there can be absorbed by the factor variance being different. That's the idea. Okay, and this is also known as weak invariance. Then we did, so at any stage, let me back up, at any stage, if the significance test tells us that the model fits worse, or even if it doesn't, we can still look at the modification indices for the constraints that we placed as an indicator as to which ones broke the model. So this is one of the reasons why confirmatory factor analysis is a relatively easy way to do this thing, because modification indices are available such that we can see which ones need to be released. So if we let some of the loadings be different across groups and keep others the same, that's what's known as a partial invariance model. There was a question last time as to how partial can you have and still call it partial? There's no hard and fast rules. For the items that want to have their loadings be different, hopefully you have some sort of theoretical explanation for why that makes sense and it doesn't undermine the whole effort of what you're trying to measure. Mathematically, you only need one. Mathematically, you need one loading invariant for the two to be linked together, but conceptually, that's not a great idea. So I would say at least a majority, 2/3 should be invariant. Otherwise, you may run into problems. By the way, this is also a solution to measurement problems in which not everybody gets every item. So I was once listening to a job talk, for instance, which job was it? University of Nebraska. That's where I was at the time. And it was someone who studies cross-cultural relationships with respect to parenting. And she was talking about the results of her study, asking parents from different Central American countries about their parenting strategies. And there was an item about how often that they used time out. So this was in relative to an American sample where it's like, how frequently do you put your kid in timeout? Okay, so do we all know what timeout is? Either having been a child or doing parenting or babysitting, timeout is where your kid screws up and they have to go sit somewhere and sulk for a few minutes until they calm down. And it's punishment, sort of, it's supposed to be a deterrent, but it's not a bad punishment. Huey goes to timeout at least once every couple days, and he sits on his chair and he's angry. For instance, he was furious this morning because he did not get to pick his dad's birthday cake flavor. So, and he's also angry that it's not his birthday. So I suspect timeout will be in our future this evening. But there were certain respondents in these countries that were like, what the hell is timeout? Like, we don't do that. And so for them, they could provide an answer to the question, but it literally was not applicable. So it would be possible under these sorts of models to have certain groups, like people from certain countries, not answer that question. They don't get a loading. You could argue that that question does not measure the trait of parenting that the question measures in other countries in the same way, so it's not applicable. And it's okay if not everybody answers every question. You would just not have a loading in that group. So you can have deliberately different versions of an instrument where certain groups get certain questions that logically only apply to them. That's preferable to forcing things to be the same and not having that make sense. So as long as you have at least a core set of items that are the same items between groups and they function the same way. So the loadings work the same, the intercepts as we're getting to and others, then you're okay. But it's the common thing that's important. So partial invariance can solve the problem of items not being given or applicable to everyone. Yes. Yeah. There are certain scales. I'm trying to remember. This was from a different job when I worked at KU. The BASC is an instrument that measures child and adolescent development, and they have a child form and an adolescent form. And some of the items are the same across the forms and some of them aren't. So I had to do a whole bunch of measurement analyses using this scale to try and calibrate children onto the same latent trait who were given different versions of the scale based on their age. And so as long as at least some of the items were given to both, not every item had to be given to both groups. Because the logic was some items are only relevant to adolescents and some items would only be relevant to young children. So yes, this is a way to solve these issues. So,
When you're doing that in M plus, is it
mhm.
like I'm imagining that like your PDF with like the model one reference group on this side and the other group over here? The items themselves can be called different things, right? It's not like you're pretending like they're the same item. Like for example, if like you didn't give South American parents that one question, like is it really that like did you like pretend that item was like did you make up another timeout or another question that didn't have anything to do with timeout but you called it the same thing, or it's just a completely different set of items, it's the same number of items on the second group?
Completely different set of items.
Okay.
The code in that circumstance actually has to look a little bit different because there has to be sort of a general model that holds all possible items, and then you would have each group
Mm,
have their own submodel that only has the ones that they need.
okay.
I don't have any examples of that in this class, but I can send any of you some that need to set up an analysis like that. So there's a bunch of different ways to use group specific models and general models in M+, and it took a minute to figure it out. So I can send that to you since I know you're in that situation with respect to that. But yeah, you don't pretend they're the same. By the way, this is also a way to empirically test where if somebody changes survey items and it's like, well, they're kind of getting at the same thing, right? It's sort of the same words. It conception. Okay, don't argue based on concepts, argue based on statistics. Fix them to be the same and see if the item properties can be constrained without hurting fit. And then you have a more solid argument that, yeah, it is the same item, even if it's phrased in a slightly different way. So, yeah, good questions. All right. Other questions? So configural, let everything be what it wants. Metric, constrain the loadings, release the factor variances. Then we get to scalar, which is a test of the intercepts, not the means, but the intercepts. And so I wanted to show you the picture that I had in my head before. This is slide 17. The idea here is, let me make this a little bit bigger so we can see it together. Here we go. So these figures show every combination of metric or scalar invariance holding or not holding. So the x-axis on these figures is the latent trait, or theta, factor score, whatever you want to call it today. The y-axis is the item response. So the slope of these lines conveys the size of the factor loading. The loading is the change in the item response for a 1-unit change in the latent factor predictor. And because the latent factor is typically identified with the mean at 0, That's why the anchor lines going down to the x-axis are shown in the middle. Like so, picture 0 in the middle, and then plus or minus 2 standard deviations like we typically do. So in the first picture here, this is a scenario in which we have metric invariance because these lines are parallel. The loadings work the same way. And they also have scalar because at the same point on the x-axis, both groups have the same predicted response. So at the same latent trait, you hit the same expected y. Here's a picture where we have metric invariance but not scalar, because even though the slope is the same, for whatever reason, at the same level of the latent trait, people who are in group 2 have a lower response. So there is something else besides the trait that is causing group 1 to have a higher predicted response at the same trait level than people in group 2. So the idea here, it's not the item mean that's being constrained equal across groups, it's the intercept for the expected outcome when the trait is 0. That's what's being constrained, and it should be able to be constrained, because then what you can have is groups that differ in their trait means. So that mean differences in the trait can trickle down into item differences. That's the idea. So at this stage where you constrain the intercepts to be the same, you also free the factor means in the alternative group or groups. So what would have been item mean differences goes up to the trait level. So mean differences in the trait in turn cause differences in the means. If that's the case, then you should be able to constrain the intercepts and just have the groups differ in the factor means. Here in D is scalar invariance, because at the same level of the trait, so this is, I wouldn't say this is yes scalar, it's like non-significantly different scalar. There's a little bit of a difference, but there's not a big one. But the slopes are not the same. So metric fails because the slopes are not the same. And in picture D, we can say that the slopes are not the same and there's a big difference in the intercept. So you can have some neither or both. Typically though, if you have an item that fails metric, if the slopes need to be different, for that reason, we skip the test of the intercepts because the intercepts could be different because the slopes are different. Okay, does that make sense? All right, did I get, yeah, I think I'm caught up on the questions. Any other questions? All right, so we do scalar and figure out if the model does fit worse, which are the offending items. Then we go on to residual variance, invariance, which is called strict. And it's less of a big deal if this fails because residual variances are not the trait. So the amount of not the trait variance could differ between groups. It's less important if that's the case. And then also residual covariances if we have any. And then we get to the structural phase. So we have variances, covariances, and means. So the example that we did last week was looking at two different groups that were separate individuals, men and women. The example that I want to go over today is 7b, is a longitudinal example where I have 3 occasions of people, the same people measured 3 times. Okay, let me pull that up. Here we go. So longitudinal invariance, 6 items over 3 occasions. Example 7b is what I have here. Now, do you remember the story that I told you at the end of last week as a precursor to this? These are real data. That's why you don't have them in your example folder. This is a former student at the University of Nebraska's dissertation. So this is a great example of what you are likely to encounter in practice when invariance just falls the hell apart. So the implications of that we will talk about, as well as what that meant for what he was intending to do. So the full background story of this analysis is that this is someone who's studying different indices of, I want to say psychotic behavior, but basically different. These are people who are hospitalized for severe mental illness, and they're tracking their change over time after they've been admitted to the hospital in various measures of functioning and well-being. And the ultimate thing he was trying to do was to fit a growth model for how these latent traits change over time as a function of treatment. And so prior to fitting the growth model, because he has these latent traits, I insisted that he do an invariance analysis, and I helped him with that. And then once the data were all done, I thought, well, this will make a great class example. So I asked for the data, and he said I could have it, and so that's where we are. So the scale, the items, the indicators, that's the word I wanted, are social competence, social interest, and personal neatness, which are all things that are coded such that more is better. So these are sort of positive things that one can improve in. And negatively oriented measures of psychoticism, motor retardation, and irritability. So what I chose to do was to reflect the negative ones so that the trait was something that was good. So improvement in the trait over time as a function of treatment would be the goal. Note that each of these things itself is a subscale. These are not items. These are sum scores across items. Dun dun dun. Now, can you guess why I allowed someone to add shit up on my watch? And still graduate? Any guesses? The answer is on the screen. He has 151 people, 6 of these indicators over 3 occasions, and each indicator had like 25 items in it. So this is an example of a concession. It's like, okay, I will let you do your latent trait analysis on subscores because this is too much to have estimated simultaneously otherwise. In reality, you're going to have to make a lot of these types of concessions where you can't do everything all at once if you don't have huge sample sizes. So ideally what one would want to do is verify that the items fit into a single factor the way they're supposed to, and pending that verification, then at least you have some sort of empirical support for the sum score. But I let that slide because I wanted this kid to be able to graduate, and this was enough of a hurdle to go through. So I have named these in a way that hopefully makes this easier to follow. I have variable 1, variable 2, variable 3, variable 4, variable 5, 6 at time 1, 2, 3. So think of this as a matrix of like a 3 by 6, 3 occasions by 6 variables. And we're going to look at invariance across time. So that means that all 18 variables have to be in the model at the same time. So this is not a multiple group analysis. It's a single group that's going to have 3 factors, 1 for each occasion, each measured by 6 items, 6 indicators. By the way, M+ will allow you to do variable transformations with an option you haven't seen yet, I don't think, called define. So I did the reflection of the negatively oriented variables in here. I simply multiplied them by -1. That way, higher scores indicated better outcomes as opposed to worser outcomes. So the scaling of these things is a little bit screwy as a consequence, but it doesn't really matter in terms of the interpretation. So just keep that in mind that in these variables, they will have only negative scores as part of their possible values. We're doing MLR and modification indices. I am asking it to print only those that would be significant at an alpha level of 0.05 for a single degree of freedom modification. And so the setup for all of this would be the same across models, and what's going to change is what goes on the model syntax. So any questions on the setup so far? All right, so here's what it's going to look like. I wrote everything out so it would be clear. I had to write everything out because of the names of the way that I named these variables. So the abbreviation, like if you have item 1 dash item 24, you can only do that if the suffix of the variable has the number. But in the way that I named these, I have the v1 part referring to which variable it is, as well as which time it is for t. And so there's no way that it would know to interpolate 6 different variables for the same time. Had I named it T1 V1, then I could have abbreviated it. So let that be a lesson to you. If you want to abbreviate a list of variables, put the numbering at the end. So a lot more code in this example, but that's okay because it makes it clear. So I have 3 factors being estimated simultaneously here. I have named them descriptively time 1, 2, and 3. So it's the idea of this measure of functioning as across these 6 ways of indicating functioning. And I have individual differences at the first occasion, second occasion, and third occasion as my factors. I have all the intercepts. Now, do I need to write these out? Nope, you don't have to write these. M+ puts them in there whether you write them or not. But I'm in the habit of writing out every single parameter that's being estimated for pedagogical reasons, and because we're eventually going to have to label them to put constraints on them. Likewise, do I need to write out residual variances? Nope, those are also estimated by default. Properties of the factor. Do I need to write these out? Factor means and factor variances. Yes, I have to write the factor variances for sure, because I'm identifying the model by fixing all 3 factor variances to 1. I have to do that because each factor is its own separate thing at this point. They're not linked together. Factor means fixed to 0 is a default, so I technically didn't need to write that, but I'm writing it here for clarity. So the model is identified such that the factor means are all 0, the factor variances are all 1. That way I can estimate all of the intercepts for the items as well as all the loadings for the items. So factor means go with intercepts, factor variances go with loadings. This width line right here, that is giving me all possible covariances among my factors. So rather than writing them out in each pair, this is a shorthand. If you list a series of variables with and then the same series of variables, it's all possible combinations. So that can save you some time. Did I say that factor means are default with 0? Yes. In M+, factor means are default estimated fixed at 0. Factor variances by default are estimated, which is why you do absolutely have to write that line that fixes them to 1 instead. Okay. Now this stuff down here, each of these lines pertains to a particular indicator. What that is allowing is that indicator's residuals to have a covariance with that same indicator at a different occasion. So there may be something about item 1, a particular response that you give that has to do with just how item 1 was asked. That makes sense to have a residual covariance for item 1 across time. That there's some other reason why the items are related besides the trait that has to do with whatever it's asking about. So in longitudinal invariance models, people do this by default. Like no one will say a word. You just throw that in there and you leave it there. So you can soak up all of that additional covariance that is due to which item is which. Question for the line before it, so talking about this line right here, does it matter which ones have the star before or after the with statement? Yes, the stars only go after. And the stars are implied. They're not necessary, but I'm using stars everywhere that something's being estimated just to draw attention to that. So I am estimating those covariances freely. Okay. Any questions on the code? All right, so let's see how this puppy fits. So we're estimating 75 parameters in total. I've got my HO model. That's me, right? I am the hoe. You'll never forget that. So this is how tall my model is. Note the scaling factor of 1.4. Each of these items probably has a great deal of skewness to it. H1, that is how tall the perfect model is. Question, why can't we put the star in the first part? Because M+ will yell at you. It's just a rule that the stars go after the width. So do I have to do the test that tells me whether this model fits, or does that done for me? My HO versus H1 comparison. Is that one done for me, or do I have to do that myself? This one is done for me. Correct. It's right here. The chi-square test of model fit is the difference in -2 log likelihood with the scaling correction factor done for you. So 283 is my chi-square test statistic for how much shorter my model is than the perfect model, and significantly shorter with 114 degrees of freedom left over. If I go down to the rest of the fit statistics, RMSEA, thumbs up or thumbs down? RMSEA is 0.099. Yeah, not good enough. Bad. Correct. This p-value right here is telling me the RMSEA is not less than or equal to 0.05, so it's not even close fit. How about CFI and TLI? Yeah, CFI is like ish. TLI is eh. I don't know how to spell eh, so I'd probably call that subadequate or something. These are each telling you how much better your model is than the worst possible model. So relative to a null model of no covariances. So that's why you can have a situation where RMSEA likes a model and CFI doesn't, or vice versa, because they're not telling you the same thing. They're starting from different endpoints of comparison. And I have a caveat here. No, this fit is not great, but everything he tried to do to make it better either didn't help or didn't make sense. So like a month later, I was like, fine, just go for it. Just do it, right? We're going to write it up and we're going to graduate. That is the plan. So fit ain't great and it's not going to get better. But here's my configural model. So we have the loadings for the same 6 indicators across my 3 occasions. Question, what is SRMR? I know the answer to that. SRMR, standardized root mean residual, I want to say is what that stands for, or something very close to it. Given that it has the word residual in it, that means you want it to be small. So any fit statistic that has error or residual in it, you want it to be as close to 0 as possible. Any fit statistic that has the word fit in it, you want to have as close to 1. This is, in a correlation metric, how far off on average each pair of correlations is from the data versus the model. So like you have your model predicted correlations, you have your data actual correlations, how far off on average each one is. So the model is off by 0.09 on average in a correlation metric. That's what SRMR tells you. You want this one to be less than 0.08 if memory serves. Smaller is better. So this is another eh. They're all kind of eh. So we have the loadings. These are the factor covariances, and because of the scaling of the model, these are correlations. So the same trait is being measured over time. We would expect the correlations to be positive. By the way, these three parameters right here, this is why you can't do a longitudinal analysis with a multiple group model. Like what we did with the men model and the women model that were separate but simultaneous, I can't do a time 1 model and a time 2 model in the same way because I have to let the factors be correlated because they come from the same person. So another way of thinking about these covariances is a model that has a multiple group setup instead constrains these to 0. So by estimating them, letting them be free, that's 3 additional parameters that we need at a minimum to address the dependency in our data. Some of you remember that word. Dependency means correlation. The idea that these 3 factors come from the same person, they're probably going to be related because they come from the same person. We have to set up the model to allow that to happen. Likewise, the items, each item has been answered 3 times. So we would expect some degree of correlation across the items. And in this case, actually, it looks like the residuals are not significantly correlated. The last column is the p-value, but we would tend to leave them in. So if you are looking to save parameters, you might be able to get rid of them, but most of the time in longitudinal invariance, they would just let you have them. And then factor variances all fixed to 1. Factor means all fixed to 0. And here are my intercepts. Note items 4, 5, and 6 are negative because of the reversing that I did. So those don't have direct meaning, but they have relative meaning. So these are the means of the items, and it looks like, for instance, item 1 grows over time. The mean grows from 16 to 17. Item 2 looks like it grows over time. Item 3 looks like it grows over time. Item 4 also grows because it's becoming less negative. And the same is true for item 5, that's not true. Item 5 is a little bit of an oddball. And item 6 grows over time. So the question that we have to answer is it because the traits are growing over time that we see these items growing over time, or is it something else? So a precursor to examining growth in the factor is all of this longitudinal invariant stuff that we got to do next. Question, is this order related to the code that you made before? The order for these covariances, you mean?
Order for intercepts.
Order for the intercepts.
Yes.
Oh, no. So the order for the intercepts is the order in which they appear on your use variable line. M+ puts its own order on things in terms of which parameters it puts out first. It has nothing to do with what you write, which is one of the more infuriating things about the output. So if you want to change the order, you change how they're listed on the use variable line. Okay. So are we ready to do this? See what happens? Okay, first step. So this is configural. First step, metric. So I'm doing 2 things differently. Here they are. At the metric stage, we fix the loadings to be equal to each other. So L1 to L6 is now on all 3 lines. So L1 refers to the common loading for item 1 across occasions 1, 2, and 3. L2 refers to the common loading for item 2 across occasions 1, 2, and 3, and so forth. So we used to have 18 loadings. How many do we have now? Yes, this is a finger question. I'm trying to change all of my course participation questions to things that you can answer with your fingers. 6 in this case. So we saved 12. However, at the same time, we also had to free the factor variance for the time 2 factor and the time 3 factor. So now all 3 occasions worth of variables are identified onto a common scale with respect to their loadings. So the time 1 factor's variance is fixed to 1. Time 2 and time 3 variance is now estimated because we're trying to see if the only reasons that they had different loadings is because we had different factor variances. That's the constraint we're trying to put on there. Everything else is exactly the same. So we saved what should have been 12 loadings, but then we had to free up 2 variances, so it should be a net savings of 10. Now, is there anything on here that tells me directly whether or not I made my model fit worse? Or do I have to do something with this information? The answer is I got to do something. Got to do something. Those of you who are using Levon, what's the thing that does the rescaled likelihood ratio test for you? I know a couple of you are. Well, you got to do that. If you're not using Levon, you got to do this. So here's a spreadsheet. This is online. You can borrow it. I have it set up so that the model that has fewer parameters comes first, and the model with more parameters comes second. So it's metric versus configural because metric is the simpler model. The part in yellow you plug in, so we fill in the log likelihood rather, the scaling factors and the number of parameters in each, and then the spreadsheet calculates the rest of this for you. Here is your test statistic in column G, the scaled difference in -2 log likelihood. So 19 is my chi-square. It's 10 degrees of freedom because I had a savings of 12 loadings, but I had to estimate 2 factor variances, so that's net 10. And my p-value, 0.0385. Oh, come on, man, so close. Now what do I do? It's worse. I made it worse. Do I give up, go home, go eat some frosting? Drown my sorrows in Pinot Grigio and graham crackers with frosting? No. Well, maybe I do, but that's not going to solve my problem, at least. It might make me feel better, but how do I fix it? Partial. Yeah, I got to know who broke it before I can fix it. So let's figure out who broke it. Our friends, the voodoo. Model modification indices. So as you might imagine, for a model that fits badly, there were a shit ton of other modification indices on the list. I am not looking at those because my goal is not to make the model fit better. My goal is to figure out what made my model fit worse of what I just did. So if we look at the suggestions here, for instance, a by statement is asking for a factor loading. And it says, you know what? I think item 1, measured at time 1, should load on the factor for time 1. And I'm like, wait, it already does. What the hell? And it's like, no. I think it should load more. Expected parameter changes in the next column, meaning it doesn't want to share the loading of the same item across the 3 occasions. It wants to have a different loading at time 1. So I have a shared constraint for indicator 1 at time 1, 2, 3. This modification index is saying that no, item 1's time 1 loading wants to be different than the other 2. And so do these other ones, by the way, but this is the biggest one. MI stands for the expected change in the chi-square that would result. So if I let the loading for item 1 be different at time 1, I would expect my chi-square difference to be better by 10. So that's what we're going to do. So model 2B Still at the metric stage, I have taken the first loading and put an A on it. Why A? Because I was already using numbers as an index, so I thought I'd add letters. M+ does not care what you call these things. If you look in the M+ directory for all the examples, they have constraints that are like 1, 2, because you don't have to label them with anything useful. But then you can't tell, like, are you fixing this at 2, or is this just the second constraint? So I try to use labels that actually make sense. L stands for loading. This is item 1, and item 1 gets to be different at factor 1 for time 1 than it does at time 2 and time 3. So that's the only change. So now we're trying to see if the model is not worse yet after releasing this constraint. So I take my new HO log likelihood, go find my handy dandy calculator, and I can do 2 different tests with it. First test I'm going to do for demonstration purposes is to see if my effort helped. So did releasing that one loading help? So relative to the model where they're all fully constrained, which is 2A, my model that has the free loading for time 1's item 1, that resulted in a chi-square improvement of 7. So yeah, that did help. Now, did it help enough? So are we at the magical not worse yet? That's configural as the baseline relative to my partial metric model that has all the loadings constrained except 1. So it's a difference of 9 degrees of freedom rather than 10. P-value of 0.44. Hooray, I win. Partial invariance. So by the way, I win because it's non-significant. So this is different than usual, right? We don't normally win because we have non-significance. But here we are trying to accept the null, baby. We don't ever say that, but that's what we're trying for here. The null is we can constrain these things equal. The way the item relates to the trait is the same across time. And none of the other modification indices were significant. So I went and looked at that list again. None of the other loadings wanted to be different. I call it good. And so I have a picture here foreshadowing what's going to happen next at the intercept stage. So these are the mean differences across items. So they're all on a different scale at this point. So it looks like most of the items improve over time except 5. The question we're after is whether or not the factor is the reason for these increases in each item across time. Okay, questions? So here's what we're going to find out then, stopping at the results, because in describing what happens, it's not enough to say non-invariance didn't hold or invariance didn't hold, we have non-invariance. It's like, well, what kind, right? That's like saying, I reject the null hypothesis. That's not the end of the story, right? Like, what happened? So we still got to say what happened. And what happened is that it looks like the first item has a stronger loading at the first occasion than at the other 2. So for whatever reason, this item is more related to the trait at the first occasion than the other 2. Item 1, just to recall, is measuring social competence. So that is more related to the trait as rated by these different therapists / personnel at the hospital where all of these patients are being administered. Okay, so we're starting with that. Scrolling down to where we were. Here we go, page 7. This is our first scalar invariance model. and I had to change those two sections. So I've added a label to each set of intercepts. So note that for item 1, the intercept for time 1 is its own thing because there's a semicolon here such that this I1 constraint only applies to time 2 and time 3. So the rules with these constraints label things is that they only hold to the section before the semicolon. So this one is not part of the constraint because it has a semicolon breaking the continuation. The second two are part of a constraint. And I just put spaces in so that these things stayed aligned otherwise. So traditionally, because the first item failed metric invariance, it's out of the tournament. So we don't put any further constraints on it by tradition. So now we're setting it up so that the remaining intercepts for the same item are equal across time, and therefore we can allow the factor means to be estimated. So the factor mean at the first occasion factor is still fixed to 0 for identification, and now the factor means for times 2 and time 3 can be estimated. So we're trying to answer the question, is it the factors that were responsible for the changes in the item means over time? Or is there something else about the item that's causing it to change independent of the factor that it supposedly measures? Okay.
Could I ask a question about the stars on the item intercepts?
Yeah.
Do they, does it matter do they all have to have stars? And like when the model is estimating those, does it like take all of them equally into account when it's giving them one item intercept?
You do not have to have stars. I'm putting them there to be explicit that these things are estimated parameters.
Okay.
But it is going to try to take, say for item 2, it's going to come up with one number that is the intercept for all 3 of those.
Okay.
If you had wanted to do start values, they would go after each of the stars. So if you have a model where estimation is taking a long time, that's often a solution that people recommend, is to start it at a reasonable place for the parameter. How do I determine start values? God. You ask God, and he, she, or they gives you start values. That's how it works. All examples of start values come from someone who's already fit the model, and they already know the answer, and that's where the start values come from. In practice, you would start with a simpler version of the model. So for instance, if you don't have enough juice to run all 3 factors at the same time, maybe you do an analysis where you have each factor separately, get the results from that, and use that as a start value to put all 3 together. Generally speaking, it's factor loadings and factors that break these things. So the intercepts you should be fine with, but you could get those just from the item means, from the descriptive data from your data set. Yeah, start simpler and build into it. So before we have 18 parameters, now 7 for the intercepts. We have, 7 intercepts before instead of 18. However, at the same time, we also had to free 2 factor means. So we had to give 2 back. So it's a savings of 18 minus 7, which is 11, plus 2 of 9. So 9 fewer parameters via these new intercept constraints. Okay, everything else is as before. And survey says, how did we do? I don't know. Go to my spreadsheet. So I'm comparing this new scalar invariance model to the previous partial metric invariance model, and it's worse by a chi-square of 55. Wah, wah. Why is it worse? So here's my modification list. So trying to figure out how I broke it with the constraints that I added. The largest one is for item 5 at the first occasion. So item 5 has its own intercept at the first occasion, but it wants to be different than the other two. So item 5 having all three constrained to be together is the problem. It's time 1 in particular that wants to be different from the other two according to this list as the biggest source of the problem. And then following that, same item at time 2. So whatever 5 means, it wants to be different at time 1. Say, okay. And the way that I do that is to break off item 5 at time 1, put a semicolon so that it's its own thing. Everything else is still the same. Here's a summary of the fit statistics because I knew I'd get tired of flipping back and forth, so I just put them in the handout. Is it still worse? Yes. Okay. Let's go over to the voodoo. Who wants to be next? Item 4 at time 1. Okay, let's do that one. Do the same thing. Break off item 4 at time 1. Is it still worse? Right at 0.05. Let's look at the voodoo. There's still one more that wants to be free for item 2 at time 1. So we add that one, split that one off, go through again, do the fit comparison, and finally, at scalar D, we're okay. If this process strikes you as atheoretical and subject to type 1 error and stuff like that, yes. Yes. It would be great if you could forecast the reasons why certain constraints would cause problems and then test those constraints in a confirmatory way, but that's not reality. So yes, if you are concerned about using modification indices this heavily to play what some people call whack-a-mole. So do you know that there's a carnival game where there's like little things that pop up and you have a mallet and you hit them? Modification indices are a lot like that because it's like one pops up and you hit it and then another one pops up and you hit it and another one pops up. Maybe take your alpha down. If you know you're going to be looking at a ton of these things, take it down to 0.01, for instance, rather than 0.05. So you can be more conservative in acknowledgement that this is a very much data-driven ad hoc kind of process that we're going for. But that being what it is, we finally hit the point where we have partial scalar invariance. And here's what ended up happening. On the intercept side, so we're looking at the results. So at time 1, it looks like for items 1, 2, 4, and 5, they have a lower score for 3 of the items and a higher score for 1 of the items than would be expected. So in terms of holding this thing together, like linking items in common, time 1 is attached to time 2 and 3 only by items 3 and 6 at this point. So item 3 has an intercept that's constrained equal to time 1, as well as item 6. Those are the things that are linking this together again. So we're just hanging on by a thread in terms of being able to look at factors as measuring the same thing in the same way across time. Because there's 4 out of 6 items that don't function that way. They're somehow different at time 1 than the others. And one of the things that I asked the student to do in his report was hypothesize why this might be. And it turns out that these are ratings not provided by the subjects themselves. So these are persons with severe mental illness in an inpatient facility. These are rating scales filled out by the staff. And yes, I am totally ignoring the possibility that different people are filling out the scale at different occasions, as well as one staff member filling out the same questionnaire for multiple patients. I am ignoring all of that because this poor kid had to graduate. So all of those things, right, that just pushing that aside for right now. But time one is upon admission. So these people are filling out these questionnaires based on people that they met 10 seconds ago. How they act socially, how they present themselves, whether they're aggressive, whether they're polite, all these things that they're being measured. Well, time two and time three are some amount of time later, presumably after the patient has become more familiar to the people who are rating them. So it's not that surprising that the items would function differently across time. So if you can reverse engineer some kind of explanation that is palatable to the 3 reviewers for your paper, then you can get yourself out of this pickle. Sounds like a sorority rush where they choose you after knowing you for 10 minutes. I will take your word for it because I had nothing to do with the Greek life. The only Greek life that I had in college is the one that we're talking about right now. Lambda and mu and sigma and all these things, right? No, I worked at Walmart and waited tables in college. That's what I did with my free time. So, yes, dropping out also. But anyway, so you can reverse engineer some sort of reason why this is not an unexpected result. But bottom line is that time one is being held together by 2 out of the 6 items at this point. Okay. Then amount of not the factor variance is the next step, residual variance. So I have left notes for myself here. So exclamation points and M+ is comments. I don't know if I said that before, but this is my trail of breadcrumbs for at what stage each of these things went off the wagon. So I'm starting step 4A with all of these things free based on already having been kicked out of the tournament. So these are thresholds, or nope, intercepts this week. These are intercepts that were already declared non-invariant, so we don't test their residual variances. So I have a system by which the things that it can be constrained are, and there's nothing that has to happen at the factor level. So at this stage, when you constrain your residual variances to be the same across time, there's no changes to the factor mean or variance that correspond to that. Survey says, did it fit worse? Of course it did. So we go over to the residual variances and find that the amount of variance that's not the factor for item 5 wants to be different at time 2 and 3. Okay, fine. I think I did these two in 2 steps, or I did one of them at least, 4B. Yep. So this was the only one that was left. So not the factor variance is different for item 5 between 2 and 3. Check it out. Of course, it still fits worse. Item 6 at time 1 is the next one. Okay, fine. Does it fit worse anymore? No. Okay, good. So you notice how I've named these things? Like I've got 2A and 2B for the metric models, and then I've got the scalar models that went all the way down to 3D, I think. And then the residual variance invariance models that were 4. I used to do a project for this class where I'd have students do their own invariance analyses, and I swear to God, someone got to like scalar Q once. Like it just kept going and going and going. And after that, I decided not to subject students to that anymore because it's a tedious activity. There are programs, by the way, in the IRT world that will figure out this sort of algorithmic which ones can be constrained and which ones can't be for you. It will run through combinations. So there are more efficient ways of tackling this problem, but this sort of shows you the mechanics of how one would get to where partial lies by brute force model comparison. So here's the final model that we go into at the end of the measurement and variance round of the tournament, where only one of the loadings is non-invariant. So that's the critical thing. We can say with some confidence that this trait is being measured the same way by these items. Item 1 is more related at time 1, but otherwise it's the same. With respect to mean differences in the factors, those hold together reasonably well across 2 and 3. Only 2 of the items hold together at time 1, and then there's some scattering of amount of not the factor variance being different, but who cares? Then we get to structural invariance. So structural invariance, step 1 here, fix the factor variances to 1. So they were free. Now we're putting on a structural constraint asking, does the trait vary to the same extent at time 1 as it does at time 2 and time 3? And the answer is no, it's fine. So previously, let me find the numbers that go along with that constraint. There's means, where'd variances go? Oh, here they are. So factor variance at the end of the measurement invariance tournament was fixed to 1 for identification at time 1. It was estimated at 1.1 at time 2, and factor variance was 0.9 at time 3. What I just found out is that those numbers are basically the same as 1. So the extent to which people differ from each other in this trait is the same over time. Okay, how about factor covariances? So I'm over here on the right-hand side of the page. What I've done is add the F-cov label there. That is constraining all 3 factor covariances, which all 3 possible, 1 with 2, 1 with 3, 2 with 3, to 1 number. Previously, those factor covariances were, let's see, where are they? They're right here. So they were 0.84, 0.68, and 0.69. I'm asking, can those all be the same? Test the difference in fit, and it's non-significant, so yeah, they can all be the same. So they share a common covariance across time of 0.72, and here's the factor means that are left. And I went ahead and did a test as to whether or not those 2 could be constrained to fit to be 0, and it did make it worse. So we keep the end of the last thing here. Okay, let's see. How many of you had longitudinal with me? Did anybody yet? Try and look in your pictures. No, most of you have not. One person? Okay. So I just found a model where across time all the variances are the same and all the covariances are the same. You will find out in longitudinal that the only way that that can happen is if everybody changes the same way. Parallel slopes creates a pattern of variance that's the same across time and covariance that's the same across time. Everybody changes the same way. The whole point of this poor kid's dissertation was to predict individual differences in change as a function of X, Y, and Z covariates. We just found out that there are no individual differences in change because structural invariance held. Rah, rah. So could we say that the relative differences in the trait are the same over time? Yep. Everybody grew by an average of 0.28 standard deviations of the factor from time 1 to 2, and then they grew up to 0.52 standard deviations of the trait, and these are in fact different numbers. So everybody grew the same. So there wasn't going to be any individual differences in change. What did he do? Say it with me. Wrote it up and turned it in. That's what he did, because it ain't his fault that this did not shake out. Kelly, you may have to do the same thing. You may have to write it up and turn it in. So this is a good example of when you may not want structural invariance to hold versus when you do. In a growth model context, you do not want structural invariance. You do not want your factor variances to stay the same over time. You do not want your means to stay the same over time, because that means you don't have any growth. But you will write it up and turn it in regardless. Okay, questions? And by the way, I am teaching longitudinal again in the spring if you all want to come party with me in my basement with my frosting. All right, that's it for today then. Thanks for coming. See you Thursday. Let me know if you need anything. Pieces.